Okay, hello everyone. We're gonna continue our class. So last time we were talking about manifolds with boundary and also orientation. So I left as an exercise some a fact, but I actually want to say a few things about it because it is very important. So last time I said, if you have a function from a manifold x to another manifold y that is smooth and x has boundary, x and y potentially have boundary, and you take a point, a regular value of the function in the interior of y, regular value, and then of f, and also a regular value of the boundary of f, which, remember, this was the value of the function restricted to the boundary of x. So if a is a regular value of f and of the boundary of f, and this is the same thing as saying that f is transverse to a, and the boundary of f is transverse to a, then the preimage of a is a submanifold of x with boundary, and the boundary is exactly the intersection of a with the boundary of x. So that's the same thing as the preimage of a by the boundary function. Okay, so I said, this was a proposition. I didn't give a proof, and I left it as an exercise, but I think, it is maybe good to say a few words. It's not completely obvious. So let's prove this before we actually continue. So, or at least let me draw a few pictures and show you how the proof goes. So, basically, if you just know that the f is transverse to a, if a is a regular value, then you can look at the preimage of a, and that will be since a is a regular value, you can look at just this preimage of a, and this will be a submanifold, more or less. I mean, basically, it is a submanifold, but what you don't know is you don't have any control over the boundary. So basically, what you can do, to prove this is the same thing that you can do in the case with no boundary. So you just sort of take a point here, and then you use the implicit function theorem to say, basically, because f is a local submersion near, so if you have this condition, then f is a local submersion near x, and then, by the implicit function theorem, you can basically, write, you can basically show that in the neighborhood of x, that being the preimage of a is the same as, being on a, you can choose a chart so that you are on a linear space. So, that will give you, basically, there is a chart such that near x, you get taken to a, even only if you are in this linear space. I mean, and then when you look at the image of the chart or the preimage of the chart, then you have a little chart for your submanifold W. Okay, so this is something we did at the very beginning of the class, of the course. And that doesn't say anything about the boundary. And if you happen to be on the boundary, and so I guess that's kind of an important point. So if you happen to be on the boundary of x, then remember everything, the smoothness condition means that you can always extend it a little bit. So you can take your chart in Hn, and now you have a smooth function on Hn, and then because it's smooth, it means that you can extend it in a little open neighborhood. So now you see your Hn inside of Rn, and you play the same game, and you will find a piece, a submanifold that's there. But basically now you don't, in principle, you don't have any control of it. So like you don't know, for example, if this submanifold intersects this hyperplane transversely or not. In particular, it could look like that, or it could look like this. or it could do something like this. Like there are many things you can picture it doing. It doesn't have to be contained. And then now, the question is, how do you actually get a submanifold that has a nice boundary, where the kind of the boundary of the submanifold is indeed the intersection with the boundary of X. Something that's not the example that I gave you last time, which was like the function f of xy equals x. That function here from H2 to R was not good for this example, remember? Was not good for this proposition because the preimage of 0 is a submanifold, but because 0 is a regular value of f, but when you look at the boundary of H2, then it's not, it doesn't work. So this example is not good. And so how do you continue the proof? It's basically just looking at this example. What you do now is you look at this submanifold and you look in charts. So, you can think of that your function f in a chart is just looks like a function that goes from Hn to Rm in a chart. So then you have the preimage of A, is some submanifold of Hn. And now what you do is you project this to the first coordinate. So you look at the projection from W. So this is just the P. Well, to be really precise, you have to kind of extend the manifold a little bit. So you have to extend the function to an open neighborhood, and you actually, instead of just looking at Hn, well, let me just keep it like this, but I'm going to just say with words. So you have to extend the manifold, the neighborhood a little bit. So your W actually goes a little bit, potentially a little bit outside Hn. So it's in a neighborhood of this point. And you look at the projection from this W to R, which just gives you the first coordinate. So this is the projection to the first coordinate. Okay, so what you really want is, you kind of want to just take the W intersected with Hn, so because your W could potentially go outside. And the point is that the intersection of W with Hn is going to be exactly pi inverse of 0 plus infinity. Because, the projection to the first coordinate is just this. So you want to look at what has the first coordinate greater than or equal to 0. And the point now is, if 0 is a regular value, the point is that 0 is a regular value of pi. 0 is, so it's the projection restricted to W. 0 is a regular value of pi if and only if or if and only if, I guess, yeah, so say that, you are at a point, well, okay, so what I want to say is the following. So X, so if you take an X in W, so X is a regular point of pi if and only if X is a regular point of the boundary of F. Okay, so this is kind of the little result that you need to understand. So basically, if you are trying now to look at this projection and to see that this is that this X is a regular point, and for all regular points, if all X is a regular point, then 0 is a regular value. That's the same thing as saying that this X is a regular point of the boundary of F. And this is a simple calculation because, so if you're not a regular point of pi, that means that the derivative of pi is 0 because it's a real value function. And then that will mean that the tangent space to W is contained in this hyperplane here. So, basically, this green thing, if X is a critical value of pi, that means that d pi at X is 0, but pi is linear. So this is the same thing as pi of X is 0. So that will imply that the tangent space to W is actually contained in the tangent space to the boundary of your Hn. And this here will give you a contradiction between being a regular point of f. So this will imply that x is a critical point of the boundary of f. Okay, this is just by some simple linear algebra. Okay, so this is the case, exactly this case here, that the non-example that I gave you last time. But this is true in general. So so anyway, so if we have a regular point of the boundary of f, then we have a regular point of pi, and then now basically it's just the result that I had mentioned before, which is if you take a regular point, a regular value of a function, and you look at the pre-image from 0 all the way to plus infinity, then you do have a manifold with boundary, and the boundary is exactly the pre-image of 0 of the regular value. Okay, so this is the missing step that I didn't mention last time, but I think it's worth saying. Okay, any questions about this? All right, so that's it. Now let's go back to what we were saying last time. So how to orient? So last time we were talking about, the last thing we said was, if we have a manifold with boundary and there is an orientation on the manifold, then that induces an orientation on the boundary. Okay, so let me remind you how you did that again. So if you have a X is a manifold with an orientation, so an oriented manifold with boundary, then what we showed last time is that the boundary of X admits a natural orientation. And the orientation was given like this. If you have, for a point on the boundary, you look at the outward normal, the outward pointing normal, and basically, the outward pointing normal, if you take the direct sum with the tangent space to the boundary, that gives you the tangent space to the whole manifold. And you said, basically a basis of the tangent space to the boundary is oriented if and only if, when you put the normal first and then you put the rest of the basis, that's an oriented basis for X, for Txx. Okay, so that's what we did last time. And I gave an example. I gave the example of the ball and this, and how that induces an orientation on the sphere. But now another example that kind of is the case where the ball has dimension 1. But it's actually very important. So B1, which is minus 1, 1, but we often think of it as just being 0, 1. So this is the diffeomorphism. So it doesn't matter that takes minus 1 to 0 and 1 to 1. This is your linear diffeomorphism. And this, of course, is contained in R. So this has 0, 1 has a standard orientation, which you can think of it as just kind of drawing an arrow like this. Here's my 0, 1. Okay? And what I'd like to say now is, what's the orientation that's induced on the boundary? So remember that the boundary of 0, 1, this is a set of 2 points. 0 and 1. And I told you that an orientation on points is a choice of signs. So let's see how this works out in this particular case. So what does it mean here? How do we get the orientation that's induced on these 2 points, 0 and 1? Well, what we have to do is, for each point on the boundary, so let's say we pick the point, let me draw the interval again. Let's see what the orientation at 1 is. So what you have to do at 1 is you have to look at the outward normal, and then you have to look at, so, basically I have the outward normal, and then I have the tangent space to the boundary. The tangent space to the boundary, it's the tangent space at a zero manifold. So that's just the 0 vector space. And then this is supposed to be the tangent space to my, I guess this is at point X is 1. So this is supposed to be the tangent space to 0, 1, which is my R. So now I have to compare the orientation here with the orientation here, and then I have to see what it induces here, basically. So, this guy is just a zero-dimensional vector space, so the basis is empty. So what I really have to do is I have to compare the orientation on the left and the orientation on the right and see if they're the same or if they're different. So, the orientation as the outward normal is pointing to the right, and it's the same direction that the orientation on the tangent space of 0, 1 is pointing to. So that's the natural orientation of R. So that means that these two orientations agree. So the interpretation that we have is that, basically this zero-dimensional vector space, this empty basis is rightly oriented. So basically it has the sign plus. So this is the right orientation. This is the right orientation. So it has, basically sign plus. And then maybe it's easier to understand when you look at what happened at 0. So at 0, the outward pointing normal vector field, it points like this. So it's normal to 0 to this point, and it has to point away from the interval. So it's pointing like that. And over here, basically what happens is that this direction is the opposite of the oriented direction in the interval. So when you look at R times n0, and then plus the zero-dimensional space, and this is the tangent space at 0 to 0, 1. And then here you see that the orientation from the manifold is pointing to the right, and the orientation from the outward normal vector is pointing to the left. So this is the wrong orientation. So basically what that means is that that the orientation to the point is minus. So this point comes with a minus orientation. Okay, so that's what it means. It's kind of subtle, but it's very important to understand that these points, they have orientation. The orientation is just a sign. So it's not an order of vectors because the set is empty, but you really do need a sign to make sure that these things are oriented, even if you're taking the direct sum with a trivial vector space. You do need to have these signs to be able to change the orientation so that they match. Okay. So basically, this means that as oriented manifolds, you can write that the boundary of 0, 1 is 1 union with minus 0. So when I put the minus there, I just, I'm not putting the plus, but I guess you could put a plus 1, meaning 1 with a positive orientation, and then minus 0, so meaning like 0 with a negative orientation. But you often, as usual, we don't necessarily write plus every time something is positively oriented. We just kind of, we just don't write the plus. Okay? Oh, any questions about this? This is kind of subtle, but I think it's important. Okay, no questions. All right, so something else is, before the next example, I want to write down an observation, which is that if X and Y are oriented manifolds, and Y doesn't have boundary, then X times Y inherits a natural orientation. Remember that, this condition of one of them not having boundaries, just to say that the product is a manifold with boundary, because if both of them had boundary, then the product of the boundary would not be it wouldn't be a smooth part of the boundary. Usually, it's something that we call a corner. But anyway, I don't want to talk about corners right now. So we have to assume that either X or Y has boundary 0, and then the product is a manifold, and it inherits it's a manifold with boundary, and it inherits a natural orientation. And the natural orientation is simple. Basically, if you take a point X, Y, in the product X times Y, the tangent space of the product is naturally identified with the direct sum of these two vector spaces of Tx X and Tyy. Okay, and that's because if you think of a curve in X, if you think of a curve here, then you can basically the gamma T is going to be some x of t and some y of t. So you can think of the two tangents, one living in the tangent space of x and the other one living in the tangent space of y. So the tangent space of the product is really naturally identified with the direct sum, or the product, if you prefer to use that notation. So a basis of the tangent space of the product is, you can think of it as a basis of the tangent space to x and the basis of the tangent space to y put together. So basically, if v1 through vn is an oriented basis, when I say oriented, I mean like a positive basis, in the sense of the orientation chosen, oriented basis of txx, and w1 through wm is an oriented basis of tyy, then you can put them together in this order: first v1 through vn, and then w1 through wm. And this is, by definition, then we define this to be an oriented basis of the direct sum, and hence the tangent space to the product. Okay? In general, when we write direct sum of vector spaces, then if this vector space is already oriented, then the direct sum has a natural orientation, which is kind of what happened here already, like in this notation for the boundary. We basically said, giving this, and if we know the orientation in two of them, then the third one is specified. I guess here, because the product, the tangent space of the product, is the direct sum of two vector spaces, then you can, this guy here on the left has a natural orientation that just comes from this direct sum. So you put the basis, oriented basis here, an oriented basis here, and that inherits, that gives rise to an orientation on the direct sum, and hence on the tangent space of the product. Okay? All right, this is kind of trivial. It's almost trivial, but it's something that requires a definition. Like these orientation things, they can be really easy and really subtle at the same time. So it's kind of like if you can write it down, then it's the obvious thing. But you have to write it down. So you have to be able to write it down. Otherwise you can get confused and you can get the signs wrong. So let me give you an interesting example. Oh yeah, so a little a remark is that you could also do this when x or y is a zero-dimensional manifold, and that's kind of what we did in the example of 0, 1. So if say that x is the point P, is just a zero-dimensional manifold. This could be said for y too. Either x or y is a zero manifold. Then what happens to x times y? So if you have just a point times a manifold, that's clearly diffeomorphic to the manifold y. Right? The diffeomorphism is obvious. It just takes py into y. And what happens is, basically this guy here, if you choose an orientation on the point of the point P, so if you say, the sign of P is plus, then this orientation and this mapping, it will take P times y to y. This preserves the orientation, so that it's the same orientation here and here. But if the sign of P is negative, then so this preserves the orientation. But if the sign of P is negative, then when you do P times y into y, this changes the orientation. This reverses the orientation. And that's just because when you look at at this direct sum, it's kind of what happens on the boundary of a one manifold. When you look at the tangent space to P times y, this is the tangent space of a zero manifold, which is just the zero vector space, direct sum with the tangent space of y. So, the orientation of this is going to be the orientation of y with a plus or minus sign, depending on which sign you're assigning to P. Okay? So to actually, this remark is important because the next example, you see how it happens. So the next example is looking at, so suppose X is an oriented manifold without boundary. Without boundary. And let's look at the interval 0, 1, I is 0, 1. And let's look at I times X. So I times X, as I said, it's a product, so it's going to be an oriented manifold with boundary. And let's look at what the boundary is. So of course, as a set, the boundary of I times X is the boundary of I times X. So this is just, 0 times X union 1 times X. So now, if we can, you can call, X1 the manifold 0 times X, no, 1 times X. And X0 is going to be the manifold 0 times X. And of course, they are both diffeomorphic to X. And this diffeomorphism, induces an orientation, which kind of assumes, that these points are positively oriented, like I explained here. So if you look at the orientation that is induced by this diffeomorphism, then it's the same as saying I'm just choosing the points to be positively oriented. So I just look at the tangent space of X1, which is the same as the tangent space of X, and I take the oriented basis for X, and that induces an oriented basis for X1, and the same thing for X0. So the question now is, what about the orientation of these guys as being part of the boundary of I times X? So I know that the boundary of I times X as a set is X0 union X1, so as sets. But what about the orientation induced by the boundary? So that's the thing that we can look at. And basically, we already did the case where X is the empty set, but now let's do a more interesting case, which is for another X. So now if how do you do that? So suppose that you take a point of the form 1x. So this is a point in X1, and let's look at the orientation induced there. So when I can draw my picture. So here's 0, 1 times X. So if I take a point on X1, so it has the form 1x, what I have to do is I have to look at the outward normal, which points like that. And then I have to look at a basis of X1. So basically, if I look at that, then I have my the outward normal. I can just consider basically if my coordinate, if I call t the coordinate on I can just think of the tangent space at 1x of I times x is just the tangent space of 1 times the tangent space, or plus tangent space of x, and I can just take my ddt here at the point 1, and this points outside, points outwards. So you can see that if I just take this guy and then I take an oriented basis of x, that is an oriented basis of I times x. So basically, because this guy here is at the same time it's an outward normal vector field, and at the same time it is positive. It is oriented in T1 of I. Okay, so it is pointing in the same direction as R, as the Euclidean vector in R. So what does that mean? That means that for this point, the orientation of x1 as part of the boundary of I times x coincides with the orientation of x1 that's induced by x. So, again, maybe it's easier to see when it doesn't coincide. So if you look at the point on x0, so point of the form 0x, then I guess it's more interesting, because here you have t0i times txx. And if you want an outward normal vector field, you can choose, for example, minus ddt. So minus ddt at 0, and then v1 through vn, that's an oriented basis for the boundary. But that has a negative sign. That's not an oriented basis for x0. Yes, sorry. This is an oriented basis for the boundary, but this is not an oriented basis for the product. So that means, basically that this boundary point, the orientation of x0 that comes here is going to come with a negative sign. So, basically, that means that the orientation on x0 as part of the boundary, as a subset of the boundary, so the boundary orientation is different from the orientation of x0 that's induced by the diffeomorphism, by the induced by yeah, so there we go. So that means that, we can basically write this guy, the boundary here, we can write this as like this x1 with a positive, with the same orientation, that x1 naturally has, union with minus x0. Okay, so you have to switch the orientation of x0 to really have something on the boundary. Okay, so yeah. So in other words, if you come here, if you want an orientation on the boundary, let me say this one more time. You have to start with something that's outward oriented here, and then you have to put something that's you have to fill up the base. Whatever base says you get here, that has to make this thing on the left positively oriented. So if you put a basis here that's positively oriented in x, then that's going to be negatively oriented for I times x, so that doesn't work. You have to do something that's negatively oriented in x to get something that's positively oriented in I times x. So that's why you have the opposite orientation. But I guess, the point is that we have this inequality here, or this equality. Okay, so this is something that's going to come up a few times today, and just something that will come up if you study topology in general. Okay, any questions about this? No? Okay, so now we're going to continue orienting things. Now we're going to orient pre-images of manifolds. So I guess, I'm going to call this a proposition. So let x and y be manifolds, and w be a submanifold, such that it doesn't have boundary, and then y doesn't have boundary either. And let f be a smooth function, which is transverse to w, and such that the boundary of f is also transverse to w. That's the condition that we wanted to say that the pre-image was a nicely behaved submanifold. Okay, so then suppose that x, y, and w are oriented. Then the preimage of w has a natural orientation. I guess you can think of this as two things. First of all, the preimage of w is orientable, which is not obvious. But second of all, as you see in the proof, there is a natural way to get an orientation on this preimage of w. Okay? All right, any questions about this before we prove it? Yeah, this is nice because, I told you it's not very easy to construct orientations. It's not very easy to construct manifolds. And I said, well, this idea of taking the preimage of regular values or preimage of transverse, using a transversality condition, looking at the preimage of submanifolds, you construct manifolds. And also, if everything that you start with is oriented, then you construct oriented manifolds. So in the case, for example, that W is just a point, then every point is orientable. You can just put the orientation plus, and then the preimage of the regular value will have a natural orientation. So that's something else. If you actually if you have a function from Rn to Rm, and you have a regular value on the function, then the preimage is orientable. I guess that's something nice to know. Okay, so I guess let me just say this as a corollary. Corollary is that if you have a function from Rn to Rm, and A in Rm is a regular value, then the preimage of A is orientable. They have the natural orientation. Because, of course, Rn and Rm have natural orientations. Okay? All right, so let's look at the proof of the proposition. Well, let me give names to the dimensions. So let n, as usual, I'm going to let n be the dimension of x, m is the dimension of y, and I'm going to say k is the dimension of w. And I'm going to write the preimage q, so this is going to be the preimage of w. And then by the dimension count, the dimension of q, we know the codimension of q is the same as the codimension of w. So the dimension of q is n minus m plus k. Okay? All right. So now let nq be the normal bundle. The normal bundle to q, or the normal bundle of q. Remember, that you can always do that by choosing a Riemannian metric. So that means that for every point q, x and q, we have the normal bundle plus the tangent bundle equals txx. Okay, so the normal bundle is a complementary subspace to the tangent space. And it doesn't really have to be normal for what I'm saying, like it doesn't have to come from a Riemannian metric, it just has to be complementary. But the easiest way to choose a complementary bundle is by looking at the normal bundle. Okay. So, all right, now we know that because the preimage, the Q is the preimage of W by F, then we know that when you take the derivative of NQ of Tx, this has to be contained in the tangent space to Y, to W. It actually, in fact, it has to be equal. Okay, So now my claim is that when you look at df restricted to n to the normal bundle, that this is injective. So can you see why? Well, that's because, we're assuming that f is transverse to w. So that means that, df x of txq plus, no, txx plus the tangent space, this goes into the tangent space of w at the point f of x. So here, this is the transversality condition. Okay, so then but txx is the normal bundle plus the tangent space to q. So this, basically now this implies that the tf of the normal bundle, well, when this guy has a normal bundle and has the tangent bundle, but the tangent bundle, it goes into the tangent space to w. So if you just take the normal bundle, that together with the tangent space to w, that has to span all of y. Okay? So this is because, this guy here had something here can be written as normal, something in the normal bundle and something in the tangent bundle. And then in the tangent bundle, it's going to go over here. And the normal bundle, it goes over here. So we do have this this other equation. And then now we just look at dimensions. Okay, so what is the dimension of the tangent bundle, of the normal bundle? The dimension of the normal bundle is the complement of the dimension of x. So this guy has dimensions. So let's look at the dimensions. This guy has dimension m minus k. This guy has dimension k. And this guy has dimension m. Okay? This is the normal bundle to q, not to x. Okay? Because q, look, has dimension n minus m plus k. So the normal bundle has to have dimension complementary to that dimension inside of x. So it's n minus this thing. So, the dimension of the normal bundle has to be n minus the dimension of q. So it's m minus q. Okay. So look at the dimensions. So if you have the image of a vector space of dimension m minus k by a linear transformation, that has to have dimension at most m minus k, and it has the same dimension exactly when the transformation is injective. So because the dimensions have to add up, then the dimension of this guy, I mean, they don't have to add up, but they have to be at least m. So that means that this the image of the normal vector space by df has to have dimension at exactly m minus k, because it has dimension at most m minus k. So then the dimension of this guy has to be exactly m minus k, which is the dimension of the domain. So dfx is injective. Okay, so in particular, like now this actually has to be a direct sum. So this guy has to be a direct sum. And then now, like I told you, if you have an equation of vector spaces with direct sums, then if you have all of the spaces oriented except for one, that induces an orientation on that one space. Okay, so here, what is oriented? What do we know is oriented? We know this guy here is oriented and this guy here is oriented. So that means that we get an induced. So these guys here, they come with an orientation from the hypothesis. So that means that induces, we get an induced orientation here. on the image of the normal bundle. Okay, so how do you do that? As usual, as I said, if you choose a basis for this guy, so v1 to vm minus k, and then you choose a basis w1 through wk, and then you say that this basis here is positive if when you put this guy with a positive basis here, you get a positive basis of the whole thing. Okay, so it's the same thing that I said before. Is that clear? Any questions about that? Okay, that's how you find an oriented basis of this guy. But because df, when you restrict it to nq to the normal bundle, this guy, this linear transformation is actually an isomorphism to its image. So this is an isomorphism because it's injective. So when you look at it, when you look at this the image, then you have an isomorphism. So the isomorphism, of course, induces an orientation also. So an oriented basis here is going to induce what it means for a basis here to be oriented. Okay. So I guess in other words, you say that. In other words, I guess I can spell out what I said with words. So in other words, if you take, I don't know, v1 through vm minus k, a basis of the normal bundle is positive if when you take a basis on an oriented basis of tfxw, then when you look at dfx of v1, dfx of vm minus k, and then w1 through wk is an oriented basis of t f of x of y. Okay, so that's it. And so that orients the normal bundle of Q. Okay, and then now, but that's not what we wanted. We wanted to orient the tangent space to Q. But now we use another direct sum. So we know that Tnx of Q plus Tx of Q is equal to Tx of x. And then now we use the orientation on x, which we hadn't used yet. So because x is oriented, then, so these two guys, this guy is oriented, and this guy is oriented. Now, so that means that now we have an induced orientation here. And that's it. So we were able to orient Q. And the order of the spaces up here in the direct sum is essential for the for our choice of orientation. I mean, you can change the order, and then you're going to potentially have a different orientation. But we want to keep this order, when we think about inducing orientations, at least to be consistent with each other. So I guess if you read another book, someone could decide, I don't like to put the normal bundle before, I want to put the normal bundle last. And that's okay, but that's going to be another choice of orientation. Just like when we decide to orient the boundary and we put the outward normal vector field first, you could say, what about putting it last? So what about putting the inward normal vector field instead? And those are all valid choices, but usually you have to choose one, and then the standard thing is choose that.
In one sense, do we say it's a natural orientation? What is the meaning of the word?
Yeah, I guess maybe it's not like completely natural because it involves choices, but say that after that original choice of order, then it's natural. So yeah, it's not like extremely natural, in a sense, because it depends on these choice of orders. But in the same way that the choice of the orientation on the boundary is not natural either. So maybe, natural is not the best word here, but a like fixed or a chosen one. It's natural in the sense that you make this choice of order, but then for any function, for any submanifold, it's kind of the same choice. So now it doesn't depend on the specific function or on the specific submanifold. It depends on something, a little bit. It's kind of like when you orient R2, or when you pick an orientation for the Euclidean space, is it natural? I guess when you decide that you have a Euclidean basis, then that's a natural orientation in a sense. Like it's one choice, but then it's going to work for every open subset, or So yeah, maybe the word natural is not the best, but I think you understand what I mean, right?
Right. Thanks.
Yeah, you're welcome. But that's a good question. Yeah. Okay. So that's the natural orientation. Again, it does not depend on anything about X, Y, or W. It just maybe depends on one choice of orders that you make at some point. Yeah. And then now, I'm gonna actually leave an exercise here, which is kind of interesting. So remember that if you pick F to be transverse to W and to be transverse, and the boundary of F to be transverse to W2, then the preimage is a submanifold, and the boundary is the intersection. Is basically just the boundary, the preimage of is this, right? It's the preimage of W by the boundary map. But you can check the following thing. This guy is an oriented manifold, and we have a natural orientation of the boundary. Whereas this guy now is just the preimage of some other. It's a preimage by another function of a different of the same submanifold. It also has a natural orientation. So I guess these two sides, they have orientations that are given orientations that are given, by in different ways. And the point is that they don't necessarily match. So, if X, Y, and W are oriented, then if we orient this guy and this guy naturally, and by naturally, again, by this particular choice of trivialization, then the orientations don't necessarily match. There will be a sign, and the sign is -1 to the m minus k. So this is the codimension of W. Okay, so I guess this is an interesting exercise for you to make sure that you understand what's going on with these direct sums and these choices. Okay. Any questions about this? And I guess you'll really see what happens, if you put the normal vector first, and then you kind of have to do some permutations to get the normal vector from being first to being like somewhere in the middle. That's kind of what. That's how the n minus k comes in. Okay. All right. So now we're going to talk about the intersection number. So now we've kind of concluded the more basic, or the theory part. I mean, of the manifolds with boundary and orientations, and then now we're going to start applying things. So yeah. Now we'll talk about the intersection number. Well, I guess before really defining it, I want to state a very important theorem, which is the classification of one manifolds. I think everybody probably has seen this before, but at least the statement. So let me give you the statement and kind of say a few words about the proof, and we can prove this later in more generality. So the theorem says that if X is a compact and oriented, and connected, compact and connected one manifold, then X is diffeomorphic to either 0, 1, to the interval, or it's diffeomorphic to S1. Okay, so there are basically only two compact and connected one manifolds with boundary. So it's either 0, 1 or S1. And, I guess, I can, I think the first time I gave this course, this was a problem on the exam. But, I guess I can say, I think it's maybe good to say a few words about this. Well, the proof, there are different proofs. It's not very hard, but it actually is a little technical. It's a little annoying if you want to write down all the details. This would be like a real analysis problem, pretty much. So you can kind of, I guess one way is like you cover your manifold with charts, and then you kind of have to show that if you can think about the domains of charts as just being, images of balls, which are just open intervals. And then if they kind of coincide, you can glue them together until you get a maximum chain. And, basically you show that it's going to be either this, or, either it doesn't connect at the end, or like it connects and you get a circle. So it's a little technical, but it's easier maybe to prove using Morse theory. That's what I'm going to do. So like, when we talk about Morse theory, I'll prove this theorem. But I guess, if you're eager, you can try to prove it using this thing that I said. If you're compact, then you have a finite number of charts, and you can assume that the charts are, that the domain of the chart or the image of the chart is something that, just an open interval in R. And then you look at how they can overlap, and if one of them falls into the other, you throw it away, and otherwise they will like overlap like this, and then you kind of glue them together, and you have to show that there is kind of a maximum gluing. So anyway, I'll leave this kind of thing here as an exercise, and then when we talk about Morse theory, we can prove this also using Morse theory. And if we don't assume X is compact, then the option, then it can also be, then X can be, an open interval or something that has one closed and one open. And that's pretty much it. There are no other options. Okay, if you assume it's connected. Okay. But anyway, what we're really going to use is this thing here. So if you have a compact and connected one manifold, then it's either the interval or it's the circle. All right. So now, okay, so that's the theorem. So now let's talk about the intersection number. So now let X, Y, and W be oriented manifolds without boundary. Such that X is compact and X and W are compact. Oh, no. I don't need W to be compact. So I need X to be compact, and I need W to be a closed subset. Closed subset. And I say closed subset because people often, when they say closed submanifold, they often mean a compact submanifold. So just a closed subset, it doesn't have to be compact. It just has to have the closed property. And I also want to suppose something about the dimension. So I want to suppose that the dimension of X plus the dimension of W equals the dimension of Y. Okay, so that means, that's another way to say this, is that the dimension, i.e. the dimension of X is equal to the codimension of W. Okay. So then the reason I make this assumption is that now I can look at the preimage. If I take a function, if f is a function from x to y, which is transverse to w, I can look at the preimage of w by f. And now, because of this dimension condition, what is the dimension of this preimage? Can someone tell me? The codimension of this guy has to be the same as the codimension of w, which is equal to the dimension of x. So since this lives in x, the dimension of this is just 0. So this is the condition that we need to make sure that the preimage of w has dimension 0. Okay, so this means, a submanifold of dimension 0, this is an isolated, the disjoint union of isolated points. A set of isolated points. And because your manifold X is compact, then it has to be a finite number of points. So finite number of points. And now remember that this submanifold, it comes with orientation. So even if it's a bunch of points, I didn't give an example of that, but it is. I'll give you an example in a little bit. Then it'll come with orientation. So these guys, this guy, this submanifold is oriented. So that means that this is a finite number of points with signs. Okay, so then I can define the intersection number. So the intersection number of f and w is going to be the sum of these signs. Okay. All right, is that clear? So let's see, again, how we get these signs. So how do we orient a submanifold? Remember that what we do is, we look at the normal bundle of the of this guy, but because these guys are points, the normal bundle is everything. So we don't even have to go in that direction. And basically, we just have that t, that df x of txx plus d plus the tangent space of w equals to t f of x y, and because of the dimension count, this is the direct sum. This guy here is the normal bundle because the tangent space to the points is just 0. So this is the equation that we had before when we were orienting this guy, and the one of the direct sums is trivial. So we only really need to look at this and see, what happens here is that you have three things that are all oriented. This guy's oriented, this guy's oriented, and this guy's oriented. So the point basically, I guess I call the point P. So let me be consistent and call this point P. So the sign of P is plus if this thing here, if the orientations are consistent. So the sign of P is +1 if and only if the orientations above match. Okay, so it's going to be +1 if these orientations match, and it's going to be -1 if they don't match. Okay, so another way to see it, this I'm kind of jumping over a step in the construction that I did before. So if you really want to follow the construction that I did before, you should think of this, this is the normal bundle. This is the normal bundle at P of my manifold. And then by the construction I did before, these two induce an orientation in this normal bundle, and the tangent space to X is the normal bundle to this guy, direct sum with the tangent bundle, which is just the 0 vector space. So now I have to say, well, this one has an orientation, and this one has an induced orientation from here, and then this is plus the empty set. So that means that you orient the empty set, not the empty set, the trivial vector space with a plus or minus depending on whether these two match or don't match. So you kind of can skip this extra step here and let's go directly here and just look at this equation and see if the orientations match or don't match. And if they don't match, the sign is minus, and if they do match, the sign is plus. Okay? So let's see how this works with some examples. But before that, are there any questions about the definition?
Our X manifold was compact, right?
Yes.
Oh yeah. So the sum is really finite.
Exactly. Yeah. That's why the sum is finite, because X is compact.
Yeah.
But you don't need W to be compact. You just need W to be closed. Okay, so if W is not closed, then the pre-image is going to be not necessarily closed. So but the pre-image of W is closed, contained in a compact set, so it's compact. So it's a finite number of points. Okay, so now if X and W are subsets of Y, with the same conditions, so that X is compact, W is closed, and they're all oriented, and X intersects W transversely, and the condition of the dimension holds, so the dimension of X plus the dimension of W equals the dimension of Y, then we can define the intersection number between X and W, and this is just the intersection of the inclusion function with W. Okay? I guess this is the definition. I mean, this is kind of probably what you'd imagine. So if you have two submanifolds and you want to intersect them, you think of one of them as being, you replace one by a function that is the inclusion of one of them, and you intersect that function with the other submanifold. Okay, and now we can look at examples of this, because I think now we're going to see this more clearly. So let's look at examples. Okay, so say that I have, here is X and here is W, and my Y is R2. So now we have to orient them. So R2 has the natural orientation, has the usual orientation, and I'm going to orient X like this, and I'm going to orient W like this. Remember, for a curve, I can just put an arrow, and that gives an orientation. And then the intersection of X and W is a manifold because they intersect transversely, and it's these 2 points. So now what we have to do is we have to see if each of these intersection points have a positive sign or a negative sign. Okay? So how do you see that? Well, you look at this equation and, so say for this point. So you have the tangent space to W here. Let me use a different color. Tangent space to W and the tangent space to X. And according to this equation here, first I put the tangent space to X, and then I include, which doesn't do anything, and then I look at the tangent space to W. And that order has to give me the orientation of R2. So it does. So here, if you first put X and then you put W, then you have the right orientation in R2. So that means that this point is a plus. And then when you look at this other point, then here you have the orientation from X. Here you have the arrow for W. So here you see that if you first put the X, the oriented guy in X, and then you put the guy in W, then you don't get the right orientation for R2. So you get the wrong one. So that means that this guy, you have a minus sign. Okay, so for submanifolds, this equation here just becomes TP of X plus TP of W equals TP of Y. So you have to look at the orientation on X, the orientation on W, put them together in this order, and see if that gives you the right or the wrong orientation for Y to determine the signs. So this means that now the intersection number of X and W is going to be, so I have +1, and then I have -1. So that's 0. Okay? Any questions about this? Okay, so let me give you another example, which is an example on the torus. So now let's say that here's one curve. Here's another curve. This is X. This is W. Okay. And then, of course, I only have one intersection point. They intersect transversely. And then we have to check the sign. So what's the orientation? First of all, the torus needs an orientation. And there are, of course, two ways to orient the torus. But, I guess I'm going to choose the usual one, which is the one where you think of the torus as the boundary of the solid torus. So, you think of your torus as being oriented as the boundary of what's inside the torus when you think of the torus embedded in R3. Okay, so there is no natural orientation of a surface in general, like a surface that's embedded in R3 has no natural orientation. But if it's the boundary of something, then that induces a natural orientation. So you can think of the torus as the boundary of the solid torus, and that will give you an orientation. Of course, you can also think of it as the boundary of the complement of the solid torus, and that will give you the opposite orientation. But yeah, like if you think about it as the orientation that comes from the boundary of the torus, a boundary of the solid torus, then you think of the outward normal vector field as something pointing out, and then the orientation to T2 is something that you can draw like this. This is a usual picture that you draw in geometry. So like this. So this is like the right-hand rule. Okay, so that means that if I first pick the vector in X, and then I pick the vector in W, so this basis actually is positive with respect to this orientation. So that means that this intersection point here is a positive point. So that means that I of X and W is +1. Okay, so this is what it is. If you change any of if you change one of the orientations, then you change the sign. If you change two orientations, then you change the sign twice, and then you get back to the original sign. Okay. Well, any questions about this? No? All right, so let's see a proposition that is kind of important. The proposition is the following. So proposition, let f0 and f1 be two functions. You know, now sort of x, y, and w will have the usual properties. So I guess I'm gonna let me just say this. Now I'm gonna assume that x, y, and w are always oriented. W is contained in y, and then none of them have boundary. The boundary x, the boundary of x is the boundary of y, and the boundary of w are always empty for now. And I will assume that x is compact, and w is closed inside of y. Okay, there we go. Okay, so that I'm gonna assume this. Okay, now the proposition is that if I take two functions which are homotopic, smoothly homotopic. So this means, I'll explain what this means in a bit. Smoothly homotopic. Then the intersection number of f0 with w is equal to the intersection number of f1 with w. Okay? So smoothly homotopic just means that there is a smooth map that you can you can vary the parameter and find between 0 and 1, find a smooth map. So in other words, let me write down what this means. Smoothly homotopic means that there exists a smooth function from 0, 1 times x. Oh, I forgot to say that they are both transverse. So they're smoothly homotopic, and f0 is transverse to w, and f1 is transverse to w. Then we have this property. Okay. So being smoothly homotopic means that there exists what's called a homotopy from one to the other, such that, so this is a smooth map such that f of 0 dot is f0 and f of 1 dot is f1. Okay. And I should say, you know, this is true even if they're not smoothly homotopic. If there's just a continuous map, that it is true. But it requires like a smooth approximation method that I don't really want to do in this course. But I guess you can see it in Hirsch. So if they're only homotopic, but not, you don't know that there's a smooth homotopy, just a continuous homotopy, then you can actually perturb the continuous homotopy to make a smooth homotopy. And, you know, this property is satisfying. Okay, so okay. All right, so now, how do you prove this proposition? So we're going to use a lemma, which is the following. So suppose that x is the boundary of some z, where z is a compact, oriented manifold with boundary. And suppose that f is a function from x to y such that f is transverse to w, and suppose that f can be extended to a function f from z to y such that, no, yeah, that's it. Then the intersection number of f and w is equal to 0. Well, I have to. I guess I forgot to say that I'm also assuming, for these intersection numbers to even be defined, I'm assuming that the functions, the little f's that I pick, that the dimension of x plus the dimension of w is equal to the dimension of y. Okay, so I'm using the letters consistently. I'm not changing the meaning of a specific letter. So now I picked some different kind of manifold, which is Z, and I'm saying what it satisfies. So what this is saying is if I have a function that's transverse to W, and I can extend the function to some manifold whose boundary is X, then their intersection number has to be 0. Okay, so how do we prove this? So this is kind of the first nice result. And it's actually kind of a core result, as you'll see. So so if we're assuming that f is transverse to W, that means that capital F, so since little f, clearly can be extended to this, means that f is capital F restricted to the boundary of Z, which is X. So since f is transverse to W, that means that capital F restricted to X, that f is transverse to W on the boundary of Z. Okay, so this is something I explained last time, that requiring that the boundary is transverse is stronger than requiring that it's transverse on the boundary. Okay, so by the corollary last time, a corollary to the Thom's transversality theorem, we can actually perturb f. We can find a sequence converging, but it doesn't even matter that it converges. We can just find a perturbation. So we can perturb f so that f is transverse to W in all of Z, and f is still equal on the boundary, and f restricted to the boundary is still equal to little f. So I can, if it's transverse on a closed set, I can perturb it away from the set so that it's going to be transverse everywhere, and it doesn't change on the set. Okay, so now I can, basically just choose my function to be transverse to W. And now I can look at what is the preimage of W. Okay, so this is an oriented manifold of and such that the boundary of this guy is the f inverse, little f inverse of W. Okay. But I have a sign potentially, so I have a plus or minus sign here. Because it depends on the codimension of W. But it doesn't matter. So, and what is the dimension of the inverse image of W? So what is this? Well, now we have to, to just look at the dimension count. So we know that the codimension of this is equal to the codimension of W, which is the dimension of X. And this, the dimension of X, is the dimension of Z minus 1. So this implies that the dimension of the preimage of W by big F is equal to 1. So F inverse of W is a compact manifold. Compact one manifold. And it better be, because the boundary is the preimage of W by F, and we already know, that the preimage of W by F, by little f, is a bunch of points. There's a finite set of points. So this is a compact one manifold. So that means that this is a disjoint union of closed intervals and circles. So this guy is a disjoint union of copies of closed intervals and S1s. And then, what is the boundary of this? So the boundary of this guy with sign, so this is going to be, first of all, an even number of points. So is an even number of points. So for each S1 component, you get no boundary points. And for each 0, 1 component, you get 2 boundary points. But as I showed you before, the boundary of this has 2 points, one of which has a plus sign and one of which has a minus sign. Okay, so that means that if you look at the number of points the number of x, well, yeah, so the number of points in this boundary such that the sign of x is positive, that's the same as the number of points such that the sign is negative. And that's going to be also true for little f inverse of w, because they have the boundary of big F inverse of w is equal to little f inverse of w, but the signs might be switched. But it doesn't matter. This will imply that the number of points in the pre-image of w with sign plus 1 is equal to the number of points in the pre-image of w with sign equal to minus 1. So that means that, if you look at the intersection number of f and w, which is just the sum of all the signs of p, where p belongs to this guy, I have as many positive signs as I have negative signs. So this number is 0. Okay? So one more time, let me say what the result again. So if we have a function that extends, a function whose domain is x, and the function extends to a compact manifold that bounds x, then the intersection number of f and w is 0. I mean, provided that the dimensions, of course, match. Otherwise, we haven't even defined the intersection number. Okay? Are there any questions about this? So now we can prove the proposition. So proof of the proposition. Remember what the proposition said? The proposition just said that if F0 and F1 are homotopic or smoothly homotopic, then they have the same intersection number with W. So now, remember we are back to F1 and F0, which are maps from X to Y, which are homotopic, smoothly homotopic, and both transverse. F0 and F1 are both transverse to W. And now you want to compare F0 to F1. And now, what you do is you look at the following things. So you can think of the manifold Z to be the product of the interval with X. And since F0 and F1 are homotopic, that means that there exists a function, capital F, that goes from 0, 1 to x. From 0, 1 times x to y, and such that, f on the boundary, f restricted to the boundary. Oh, actually, let's remember that, the boundary of 0, 1 times x is basically, 1 times x union 0 times x, but with a minus sign, with this opposite orientation. So that means that, and we have that f of 0 dot equals f0, and f of 1 dot equals f1. Okay, so now by and so basically, in other words, the boundary of f, is basically f restricted to the two boundary parts. So this is basically f1 on 1 times x, and this is f0 on 0 times x. Okay, so now applying by the lemma above, we have that the intersection number of the boundary of f with w is 0. But now, the intersection number of this, you're gonna count a bunch of points that are that come in the intersection of f1 and 0, and then f1 and w, and f0 and w. So this is going to be, it's going to have a term like all the points that intersect where f1 intersects w, and all the points where f0 intersect w. Okay, actually, let me write everything on the same line to be clear. So we have that, the intersection of the boundary with w is 0. So then the points that are here, on the boundary of f, the intersection of the boundary of f and w, are going to be the points on f1 intersected w and f0 intersected w. So you have the term of f1 w, and you have the term on f0 w. But because of the orientation here, one comes with one sign and the other comes with the other sign. So this one, say, comes with a positive sign, and this one comes with a negative sign. And that's basically what you get. So this one is f1, so it has the same orientation as f1, and this one has the orientation of minus f0, has the opposite orientation of f0 here. So that's why we get then, we get that I of f0w is equal to I of f1w. And that's it. Okay? So with the lemma, the proposition is very simple. But I mean, if you wanted to prove the proposition directly, you could do it. And it actually, you can draw a nice picture, So if you if you don't want to apply the lemma and you want to just prove the proposition directly, you can just say, well, if f0 is homotopic to f1, then you have this homotopy. And then you look at the pre-image of the homotopy of w by the homotopy, and that's going to be a compact one manifold with boundary on the boundary has to be on 0 times x union 1 times x. So that means, that your if this is your 0, 1 times x, you have to have, your boundary is going to be, something, I don't know. Could be something like this. Then it could be like this. It's a one manifold, compact one manifold with boundary on this. So that means, when you count the number of points, you're going to have the points on 1 times x and the points on 0 times x. And if you take into account the orientations, it's going to be the points here with the sign coming from f1, and the points here with the opposite of the sign coming from f0. And the total number of points is even, or it has to be 0 if you count orientations. So you can prove directly with this picture, but this is just applying the theorem that's the lemma that's a little more general, where you take any manifold that's the boundary of something, and you say that the intersection has to be 0 if you can extend the function to the inside. Okay? So just to finish, as an application of this proposition, then now, if f is some smooth function, that's not necessarily transverse to W, and with the same, dimension conditions. Then what's great is that we can still define the intersection number of F and W. And how do you do that? So you take G, which is homotopic to F, such that G is transverse to W. So by the Thom transversality theorem, you can find any of those functions that are converging. In particular, they are all homotopic. So you just take one that happens to be transverse. By the Thom transversality theorem, you can find a sequence that's transverse. And then you just define I of FW to be I of GW. And by this proposition, it doesn't matter which one you pick. So if you pick another one that's homotopic to F, that's transverse to W, the two of them are going to be homotopic as well. So they are going to have the same intersection number. So this is well defined. Because if G tilde is homotopic to F and G tilde is transverse to W, then G tilde is homotopic to G. So by the proposition above, the intersection number of G and W is equal to the intersection number of G tilde and W. Okay? So, that's very nice. We have, we define intersection numbers for non-transverse intersection, when the function is not transverse to W. Okay? So, here are some examples of this. So I'm going to give, very similar examples to my examples before, just for inclusions of submanifolds. But, if you can cook up examples that are not inclusions, that are just a little harder to describe. But let's say, my X is this, and my W is this. So what is the intersection between X and W? Of course, you can do the same thing for submanifolds. So what you have to do is you have to homotope one of them. So you homotope the inclusion, which is the same thing as homotoping, the embedding of X into the manifold, into R2, so that they intersect transversely. So there are, two ways of doing this, kind of two different ways. One is you can actually separate them. Or you can have this. And we've already seen the intersection here is 0. And of course, the intersection here is 0 because it's an empty sum. So it has to be the same number. It's to be consistent. Okay. And then the other example is when we had a torus. I can make that thing not transverse to make it interesting. I can have this as my X, and then I can have my W like this. So now, they share that the tangent space goes, tangent space is shared here. And then now, how do you make this, what's the intersection here? If you just perturb this so that they're no longer horizontal, and they no longer have the tangent space coincide, you can do that in two ways. You can perturb it like this, or you can perturb it like this. So let me do the more interesting one. So you have this one, you can perturb your W like this. And of course, you can perturb your W like this. And, you can see that in this case, again, you're going to have just one intersection point, but now it's a transverse intersection, and you have a plus sign. And here, you get 3 transverse intersections, And this one is plus, this one is minus, and this one is plus. So you see that the total intersection number is 1 in both cases. And here you see very clearly that you really need to put signs on the intersections. You know, if you just count the total number of intersections without putting signs, then the numbers would be different, and you wouldn't have this invariance property for homotopies, which is very, very important for all the applications. Okay, so let's stop here for this lecture, and we'll continue with the next one and talk about degrees.